Hello,
Yes, sir.
and my screen
Yes,
completed.
sir. We can see source of contaminants in water.
Okay, so here we discuss about just closing the windows.
স্যার আমাদের কয়েকজন মেবি ওয়েটিং আছে স্যার, জয়েন করতে পারছে না।
So I already made many of you as a host and co-host. So hope you can now change the status of others. If anybody entered into the working room, so please admit them. Okay, shall we start? Can you hear me?
Yes, sir.
Okay, shall we start?
Yes, sir. We can start.
Okay, so in water system or in our water resources, if we just consider that what are the sources that can contaminate our water resource, or what are the point or non-point region that that can that can pollute our system, water system. Here is some examples, or most of the examples are included here. It is this figure is actually accumulated by a US EPA, and I just took from them. And here you will see the municipal well. It can be also a source. Spills, accidental spills, sanitary landfill, gas station, underground storage tank, landfill station, urban runoff, industries. Yeah, they are discharging something, and septic system, agricultural chemicals, pesticides, whatever. All those can be contributing to the groundwater pollution and surface water pollution. At the same time, we also see that their saltwater intrusion can be a source of pollution. Like it can intrude to the surface water system as well as to the groundwater system. So here is a list: septic tank, injection well, landfill, underground storage tank, waste tailing, waste disposal site, pipelines, pesticide, fertilizer, acid mine drainage. Acid mine drainage is a special kind of pollution source, while people do mining in mainly in gold mine and some other metal mining case. They use different kind of acids to purify the ore materials. So that is also have a significant impact, and it is quite a significant source in many other African countries, and as well as in South Africa, in China, in many other countries as well. Production well, monitoring well, excavation, all those also can be a source. Sea water intrusion, groundwater source, groundwater surface water interaction. So if there is a surface water, there is a surface water. If it is contaminated somehow with the contaminant, in that case also it can be a source to the contamination to the groundwater case. So from all this perspective, what do we do as a water quality manager or water quality scientist? We usually get this kind of data sheet with some sample ID. The data could be look like this one, or could be look like this one, or could be some data will be missing in somewhere, or some data are not detected. Like this kind of things also can happen. It's an example case. So here one data, if we just consider, here is temperature is 23 degree, pH is 7.94, electrical conductivity is 590, redox is 141 millivolt, dissolved oxygen is 3.2, alkalinity 165.9, chlorine is 12, 0.12, chlorine 49.4. All are given in milligram per liter. So you see bromine, nitrate, phosphate, sulfate, calcium, magnesium, sodium, and potassium. Indeed, you will find that these are the major ions and parameters are usually tested in most of the facilities while we are judging for the water quality. Sometimes there is iron also being tested in many instances. Sometimes you will find that TDS is there. Sometimes you will find only EC or only TDS, either one. Sometimes you can find a both. Redox is one common kind of parameter. You will find it usually people used to test it, but in many instances it also could be missing. So here is all the parameters, and at the end, if we wanted to compare it to each other, or if we wanted to find it, what is the correction or what is the problem with the datasheet, in that case, we need to go for a evaluation. In that case, we need at first we do the equivalent weight. Then maybe in some cases it is milli-equivalent weight per liter, means per volume. Sometimes we need to convert it into molarity, means milli-equivalent weight per kg of water. So we convert it into milli-equivalent weight per liter. Here is the example. In that case, we just got that the cations are 17.10 and anions are 17.50. Indeed, it is not the real example. Maybe it is just a case. Yeah, for calcium we got 2, and the weight milligram is 151. Then we have equivalent balance molecular weight is 40.08, and we got the equivalent weight. And finally, we try to get the equivalent molecular weight balance or electromagnetic electrochemical balance. There is some okay, I just wanted to come to this slide first. So to to characterize that whether it is right or wrong, in that case, we can compare it electric conductivity and TDS ratio with the TDS and sum of total cation and anion. We can compare these two, TDS and sum of total cation and anion. We can check the ratio of TDS in EC. It is just came double. It should be 0.55 to 0.70, this ratio. Ionic balance, it should be 5% is acceptable, should not exceed more than, should not exceed 5%. We can divide the EC with 100 and sum of cation divided by anion. This ratio should be 0.9 to 1.10. Means if you divide the EC with 100, in that case also you will find it should be between the EC value is 0.9 to 1.10, and sum of cation and anion, their ratio also should be 0.9 to 1.10. It is one measure, and some other is agreement between EPM and EPM of cation and anion. That's I'm just skipping it. And there is one more measure. Here is the calculated TDS and measured TDS. There should be an agreement between calculated TDS and measured TDS. How the calculated TDS can be calculated? It is given here. Calculated TDS means here 0.6 multiplied by alkalinity plus sodium, potassium, calcium, magnesium, means all those ions weight. Just whatever it is in milligram per liter, you should add it up and then divided by measured TDS. Means if you have a data that is TDS data measured in the field, then in that case you can do this kind of comparison or this kind of correction. So their ratio should be 1 to 1.2. Means the measured TDS and calculated TDS, they should be equivalent or same, or measured TDS could be a little bit higher than the calculated TDS, because in many instances you will find that some ions are not tested or skipped during the analysis. That's why their ratio should be always less than greater than 1, and but it should be between 1 to 1.2. And then the ionic balance of the sample, you already know this formula, and here we will sum up all the cations and then sum up all the anions in milli equivalent weight, and then this we will use this formula in our sample for a specific sample. Then if it is less than 5%, then we can say it is reasonable, or within the 5% range we can say it is reasonable. But if it is, in some instance you will find that it is 10 to 15%. In that case also, if it is a complex sample, means if the sample is coming from landfill leachate site or maybe highly polluted site, in that case also we will accept it 10 to 15% error. But for the fresh water or normal water sample case, it should be 5% or less. If it is negative ionic balance, in that case, obviously cation is at the front. That's why negative ionic balance means too many anions are calculated in our study, or cations are still not calculated by this time. So this statement is wrong. Too many cations is wrong. It should be, if it is negative ionic balance, in that case it is too many anions. Do you understand my point here? Hello?
স্যার আবার রিপিট করুন।
I'm just repeating here that in this equation you see that cation is at the front and anion is later. Yeah. So if you find that the ionic balance is negative, if ionic balance is negative, in that case it should be obvious that anion value is bigger. That's why you will get a negative. If cation value is bigger, in that case you will always get a positive ionic balance. Is it okay?
Yes, sir.
স্যার বাট এখানে যে লেখা আছে স্যার যে ইফ নেগেটিভ আয়ন ব্যালেন্স ইজ টু মেনি ক্যাটায়ন্স,
এখানে কোয়েশ্চেন মার্ক দেওয়া এখানে।
ওকে
মানে এটা স্টেটমেন্টটা ভুল, এতক্ষণ ধরে তো এটাই বুঝাচ্ছি।
জি স্যার বুঝতে পারছি।
হ্যাঁ, okay, so we got the ionic balance case, we got the measured and calculated TDS case, two kind of measure. We can do these things, EC divided by 100 and sum of cation divided by sum of anion. These things also we can do easily. We can do TDS by EC ratio, yeah, from our data. So these four measures are already described by now. Okay. Means how can you check the water quality data? That is, there is four method already we have discussed. One is this one, and that is this one, ionic balance. Then third one is TD by EC ratio, and fourth one is also you can check by EC divided by 100 or sum of cation divided by sum of anion. So after that we can do the what kind of source it is. That should that decision also we can make from the data. If we have the metal ion and cation anion data is available in our data sheet, in that case we can decide, or we can get an understanding that what kind of rock source are contributing to our water quality data or water quality sample. That also we can decide. In that case we need to do some kind of additional calculation. It is not too much tedious. It is just from the milligram per liter this data. We can just sum it up, means sodium, potassium and calcium. Calcium ion should be subtracted from there, and here also we do the same kind of sum, sodium plus potassium plus calcium and minus chloride. And if the ratio between these two is greater than 0.2 and less than 0.8, in that case we can say that our rock source is pelagioclase. So if it is this ratio lies between 0.2 to 0.8, in that case, we can say that the rock is from, means the water sample is coming from pelagioclase rock.
Sir,
Yes,
sir, do we have to convert into mole per liter for this calculation?
I don't think so. Just
Yes,
we
sir.
can do it with the milligram per liter. Again, second source tracking is sodium divided by sodium plus chloride. If their together value, their ratio is less than 0.5, greater than 0.5, in that case we can say halite. Its source is not from halite albite. It may be other kind of source. It could be maybe maybe saltwater intrusion or some other source could be, or maybe agricultural source. That's also possible if it is greater than 0.50. Then third one is magnesium and calcium plus magnesium. If it is greater than 0.5, in that case it is dolomite dissolution and calcite precipitation. Means the source rock is dolomite and calcite is already precipitated from into the system. That's why we are getting this kind of data or this kind of sample. Then the ratio of calcium and calcium sulfate together, if it is greater than 0.5, it will indicate a calcium source, but not from gypsum carbonate or silicate. It should be calcium source, but it's not from gypsum carbonate or silicate. So third, I think it is the fourth, 1, 2, 3, 4, fifth one. If that ratio, the previous one, it is calcium plus magnesium divided by sulfate ratio is range between 0.8 to 1.2, then it will say that that source is not from dolomite, or dolomite means the sample is already causing some kind of dolomite precipitation. The calculated TDS value is less than 500 milligram, then its source should be silicate weathering, not from other source. The ratio of calcium, chlorine and sum of anion is less than 0.8. The ratio of chlorine and sum of anion means chlorine value divided by sum of anion is, if it is 0.8, indicate rock weathering as the value of ratio carbonate, and in that case it will indicate rock weathering, and if it is the ratio of bicarbonate to sum of anion greater than 0.8, it is indicating silicate or carbonate weathering. So this deduction maybe I'll not ask, or maybe I will ask only for the last statement, last two, whether it is what kind of weathering cases it is occurring. These three statement you need to consider. So for the exam, you need to state it. You need to state that whether it is from silicate weathering, or it is from rock weathering, or it is from silicate or carbonate weathering case. You need to state only that that particular case. Last three. This one you can skip it, but it is just to let you know that whether you can maybe you can use it for your later perspective or for some other cases. So there is some errors that we have discussed in our class. There is that is very common in water sample analysis. Here is listed some other special case, like means most common source of error sources could be the broken filter, means filter is not working properly. Whenever we are doing the after taking the sample, if we come back to the lab and we need to do the filtration, in that case the filtration, if it is not properly working, in that case also may have some problem. So acidification of unfiltered sample leads to positive balance. Unfiltered sample, if you acidify unfiltered sample, in that case we will have a positive balance. Positive balance means our cation will be higher. Second one is alkalinity titration of unfiltered sample leads to negative balance. Means if you filter the sample, if you test the alkalinity without filtering, in that case you will get negative balance. Analysis of water with very low TDS lead to negative or positive balance. Means if your sample TDS is a little bit if you find that it is very low, means if it is coming from oligotrophic environment or lake perspective, in that case there is very chances that you will get some kind of analytical error or chemical analysis error, which is very common, because most of the cation or anion will be a little bit smaller value, and in that case there is very chance that you will have some kind of error. So these are the few common source I just discussed here. I can discuss some other sources, but I'm just I can skip it. So here is some presentation perspective, means how we can present our water quality data. We can do the strip diagram. Strip diagram can present all the cation and anion together in one diagram. It is very nice one. Suppose one sample here, it is calcium, magnesium, sodium are presented here. The value are, for example, in this case, we see that sodium value is very low, calcium value is really high, around 16.7 milliequivalent per liter. Magnesium value is almost 2 milliequivalent per liter. Here we see that chlorine is very low, bicarbonate is around 4 milliequivalent per liter. Sulfate is really high. Sulfate is almost 16.7 milliequivalent per liter. Other possible pair could be iron, potassium carbonate, nitrate. That pair we can add it, yeah, in this diagram. That's also possible. And we can map it, means we can present this strip diagram in the map as well. Yeah. In that case, if somebody see the map, then he can get an idea that okay, here is maybe sulfate is higher, calcium is higher, and sulfate is higher. Maybe it is calcium sulfate kind of aquifer. Here it is not that much. So here all those sodium, calcium, potassium, there sodium, magnesium, calcium, all are similar. Here maybe we can decide, okay, it is sodium is higher, then carbonate is higher, and sulfate is higher. Yeah, this way we can it is chlorine is higher. So this way we can interpret. If you just enlarge it, it is like that. Then second most popular one is Piper diagram. Piper diagram, here is the calcium in this side, magnesium increasing in this side, sodium and potassium increasing in this side together. This diagram shows all the anions. Chlorines in this side, sulfate is increasing in this side, and in this side carbonate and bicarbonate together. And if any sample fall in this triangle in middle part, we can say there is no dominant type of water, means that water is not a any kind of, means it is not a chloride kind, or it is not a sulfate kind, or it is not bicarbonate type. But if it is some sample, if it is fall in this corner here, yeah, then we can say it is chloride type. If it is fall in left corner with bicarbonate, then we can say it is bicarbonate type. If it is fall in calcium in this corner, then we can say it is calcium type. And if it again it is in here, so we can say that the specific sample is together, it is calcium bicarbonate type. So from this two, we can plot it here together. So here you see that calcium, magnesium, sodium, and potassium. So calcium and magnesium are coming together in this line. From here, it is coming in this line together, calcium and magnesium. Carbonate, bicarbonate is here in this line. Sodium, potassium, calcium, and magnesium, if their ratio is coming in this line. So here is the interpretation of the corners. So here is the projection, how we can do the projection of that specific sample into into upper diamond. So if a sample is here in this part, and another sample if we got here in this part, chlorine is here, and calcium, sodium, potassium is here, and calcium is here, and this one is for magnesium, sodium, potassium, this part together in here. So from this one we can draw a line in this upper side, and from here we can draw this line into in this upper side. It intersect here in this point, and then we can interpret it, this one, with this type. How it can say that, okay, calcium plus magnesium is here, means this block will interpret the water type for this specific sample. So if some sample fall in here and another sample fall in here, then it will intersect in this part. Yeah? So then we can interpret the result from this middle diamond. So here is the advantage or disadvantage that that the things that in with the pipette diagram we can directly interpret the result, or we can get a detailed idea about what kind of water it is. That's possible. Druop diagram is also possible to present the data using this kind of triangular scale, means total cation in this triangle, anions are in this triangle, TDS is in this triangle, pH in this triangle. Yeah, this way we can present it. And another one is Euler diagram. It is in semi-logarithmic scale. It is not in irregular scale, and this side is for cation and this side is for anions. And they plot it on the based on the scale, it is milliequivalent per liter. Here is we can see quite well. It is concentration in milliequivalent per gallon or liter, whatever it is. And here logarithmic scale it is, and cation is in this side, anion in this side. There is some other plot is available, so like radial plot. It is not. It is also sometimes people use it, and we can prepare the time series if we have a historical data for a single parameter. In that case, we can prepare the time series, just plotting the variables over time. And Box-Whisker plot that help you to plot the mean, median, mode together. Yeah, in this kind of plot, it is the mean, and it is the standard deviation also. It is showing. So that's all. So time series, these things will not come into the exam for sure. Piper plot also will not come into the exam. So the presentation things I will not ask you into the exam. So you need to concentrate on the on the part up to here.